Simply put, a wave is a transfer of energy. For example, the waves surfers ride were created by energy from wind. Sound also travels in waves, moving from the source of the sound through the air to your eardrums. Sound and ocean waves are both mechanical waves because they need a medium to travel through, such as air or water. Electromagnetic waves are also the result of energy, electric and magnetic energy to be precise. But unlike mechanical waves, EM waves do not need a medium to travel through. This is why electromagnetic waves, like infrared waves and gamma rays, can exist in outer space, while sound cannot because it needs air to travel through. We organize electromagnetic waves on a spectrum based on the distance between waves and the frequency of waves, or the number of waves that occurs per second. The faster the wave frequency, which we measure in hertz, Hz, the shorter the distance between waves and the greater the amount of energy they produce. The weakest and least frequent EM waves are radio waves, and the most powerful and most frequent waves are gamma rays. You can see them on the far right-hand side of the spectrum. If you think of it in terms of music genres, radio waves would be easy listening and gamma rays would be heavy metal. The waves at the far end of the spectrum move so rapidly and emit so much energy that they are no longer thought of as individual S-shaped waves, but rather as strong rays of energy. Think about how much energy is present in visible light, like the sun or a light bulb, and then multiply that energy by 10 billion, and you have an idea of how much power we are talking about here. Gamma rays come from radioactive sources. On Earth, they are created as a result of nuclear explosions, like when the U.S. dropped atomic bombs on the Japanese cities of Hiroshima and Nagasaki in 1945. They are also emitted by lightning and by radioactive fallout, which is the extremely hazardous radiation left over after a nuclear explosion. From pulsars to neutron stars, space is full of naturally occurring gamma rays. Since they aren't part of the spectrum of visible light, we can't see gamma rays and other electromagnetic waves like radio waves and X-rays. Scientists have had to imagine what it would look like if we could see all the electromagnetic activity in the night sky. Exploding supernovas and other gamma ray bursts, or bursters, would light up like fireworks at least once or as many as 5 times a day. The Compton Gamma Ray Observatory was a 17-ton space observatory that recorded gamma ray activity in space from 1991 to 2000. The CGRO housed 4 very advanced scientific instruments, including the Energetic Gamma Ray Experiment Telescope and the Burst and Transient Source Experiment, which gave scientists a much clearer picture of gamma rays and their part in cosmic activity. For example, they located hundreds of unknown sources of gamma rays in space and were eventually able to explain the origins of gamma ray bursts. Scientists also use gamma rays to determine if elements like iron, hydrogen, or oxygen exist on other planets. Let's review. A wave is a transfer of energy. Mechanical waves, like the waves surfers ride, or sound waves, have to travel through a medium, like water or air. Gamma rays, on the other hand, are electromagnetic waves, meaning that they can be found on the electromagnetic spectrum. Note that electromagnetic waves are also the result of energy, but unlike mechanical waves, EM waves do not need a medium to travel through. This is why electromagnetic waves like infrared waves and gamma rays can exist in outer space. Gamma rays have an extremely high frequency and are thus very, very powerful. On Earth, they come from radioactive sources like an atomic bomb. In space, they occur naturally from lots of sources, including pulsars and neutron stars. Because they're not in the visible part of the electromagnetic spectrum, we can't actually see them, but scientists imagine that if their bursts were visible, the night sky would light up like fireworks.